don't worry, that's not actually your pages going off. I saw some of you get down here get a little bit stressed when that noise happened. Don't worry, it's not, it's okay. But this was a situation I found myself in about 5 years ago now. I was working for a cybersecurity startup at the time, and the company I worked for, we used to send out fake phishing emails. So you could come along as an IT administrator, you could sign your company up, and we'd send out fake phishing emails to all your employees. And we could track who clicked the emails, and we could use that as a way to tell who needed more training on phishing. And I got this page, and I had 2 issues at this moment in time. The first issue I had absolutely no idea what caused the problem. I knew that there were more emails being sent than there should have been, but I had no idea of seeing why. The second problem I had, the problem much more personal to me, was that earlier that day, I just changed the way the email sending behavior worked. And at the time, I just discovered event-driven architecture. And obviously, as these things go in our industry, when you discover a new pattern, a new practice, a new framework, everything you then build has to use that new pattern, doesn't it? So I just changed the email sending behavior to work in an event-driven way, a more event-driven way. There was now a scheduler service and an email service. The scheduler service kept track of what emails needed to be sent. And when there was an email to be sent, it would publish an email ready to send event. That was then consumed by the email service. The email service then went off and actually went and sent the email before then publishing an email sent event, which was then consumed by the scheduler service. And in both of these events, there was a common identifier. So when that event came back, the record in the database could be marked as sent. Now, I just made a change to the structure of that email sent event earlier that day, which meant the email came back, the record never got marked as sent in the database, and the scheduler said, hey, I've got more emails to send. Email service receives that event. We get more emails. Now, I don't know if any of you ever received phishing emails. If you receive one email from Domino's, maybe you click it, maybe you don't. If you receive 52 in a row, maybe you realize that this might be not really a Domino's email. So that's what you're going to learn about in this talk. At the outset, event-driven systems seem nice and easy, don't they? Publishers publish events, consumers consume events. Everything's nice and simple, right? Until it isn't. And a lot of the talks over the last couple of days have talked about some of the ideas, the practices of event-driven architecture. I'm going to kind of focus on some of the more day 2 stuff, if you will, that kind of boring, less sexy, less exciting stuff. I'm James Eastham. I'm a developer advocate at Datadog. I'm a Microsoft MVP. I'm an AWS community builder. And if any of you have ever seen me talk before, you'll know that there's one thing I love talking about almost as much as event-driven architecture. That is, of course, pizza. Who here thinks pizza's the best food on the planet, by the way? The rest of you? Come on, people. Come on. Yeah, that's a good point, actually. Maybe I should do this in Italy and see how it differs. There was definitely less hands then than I normally see, actually, which is interesting. I should start tracking that. So for the rest of this talk, you all need to forget your day jobs, forget your Jira backlogs, forget everything else you do, because you're all now developers for plant-based pizza, Belgium's #1 plant-based pizza delivery company. And throughout this talk, you're going to work through the kind of typical software development lifecycle that you would take with an event-driven system. That starts with the code itself. How would you actually evolve the data structures? How would you actually evolve your code and deal with things? Then we're going to look at how you actually test these event-driven systems. How should you think about making sure your event-driven system works before finally looking a little bit at observability? How would you actually understand what it is that your event-driven system is actually doing when it's running in production? And as we get started with this, it kind of helps to, at a high level, understand exactly how this system works. And this is a really, really high-level look at things. All the code for this is all available on GitHub, by the way. There's some links at the end. You can go and have a look at this. There's a AWS-specific implementation. There's an Azure-specific implementation. And how this all works is that a user comes along, they want to order a pizza. They say, I want to create a new pizza. That create order request comes to the order service. The order service goes off and does some work, processes the order, and then publishes an order confirmed event. The kitchen then consumes that order confirmed event, does its own internal thing, its own internal processes, before eventually publishing an order prepared event, which is consumed by the delivery service and goes off and actually organizes the delivery of the pizza. You'll notice that the order service also consumes the order confirmed and order prepared event. That's so that when you're all sat there furiously refreshing your mobile app, making all the developers really glad they implemented rate limiting, you can get the up-to-date status of the order. So you get this first version running in production, and you're like, excellent, we're event-driven, this is fantastic. And then you start to deal with one of the #1 constants that affects all software systems. And that is change. Yes, thank you. And when you start to read about event-driven architecture, it's commonly touted that evolvability is one of the core benefits of building an event-driven system, right? Change is really easy to deal with, isn't it? Because you've got these events flying around, you need to make change, you can just spin up a new service and just hook into this new event, and it's great. And if we take a really naive example, this is an order confirmed event that you are publishing today. And you publish that order confirmed event to a topic called order confirmed. The kitchen service is consuming that order confirmed event amongst many other services. Congratulations, you're event-driven. Congratulations, you've also given yourself here very few ways to evolve this system in a really safe way. And I think it's really important to remember, and Sheen talked about this in the keynote yesterday, that the events you publish in an event-driven system are the API of your system. They're the public API of your system. So we should treat these events that we publish the same way we would treat a more typical synchronous API, or maybe an open source package that you publish for people to consume. What would you do if you were building an API that people were going to consume, or you were publishing an open source package? You'd use versioning. And of course, Leila spent a good 50 minutes talking about versioning earlier, so I'm not going to spend too long here. But there's a couple of ways you can think about versioning in an event-driven system. The first is, instead of publishing your event to a topic simply called orders confirmed, you can shift some of this versioning into the actual infrastructure. So instead of publishing to a topic called orders confirmed, you publish that to a topic called orders confirmed version X, version 1 in this case. And then when you need to make that breaking change, you can split these things up at an infrastructure level. Instead of publishing to version 1, you can publish, but as well as publishing to version 1, you will also dual publish and publish that same event to version 2 as well. Over time, your consumers can then switch over and start consuming the version 2 event. Now, the danger you have if you do this, unless you're really, really careful, is you end up in a situation like this, where you're supporting lots and lots of different versions of the same event. You've got lots and lots of topics, you've got lots and lots of infrastructure, you don't really know which services are consuming which event. This can become a problem really quickly. So one of the most important things to do as you start to think about versioning is be really, really clear on depreciation dates. Set a date you're going to depreciate the given version of an event and stick to that date. No matter what happens, you need to stick to that. In an ideal world, you'll only be publishing 2 versions of the same event at any one time. Now, that doesn't always work in practice, but it's a good thing to try and aim for. You've got the current version, and you've got the version that's going to be depreciated. This isn't always possible, though. Maybe you're using a messaging technology that doesn't quite support this splitting things out at an infrastructure level. Something like Amazon EventBridge, if you're familiar, where you can't really split things out at an infrastructure level. Or if you're using queuing, for example, maybe these are queues and not topics, what actually happens if you dual publish these messages to 2 different queues? Well, maybe the kitchen service is consuming the queue with the version 2 events, so that gets consumed by the kitchen service deletes that from the queue, but then you've still got that message that's sat there on the version 1 queue. That version 1 queue can start to build up and build up and build up over time. And you can also have the opposite problem, where you are processing version 1 messages, you switch over and start publishing versions 2, and then you see the same event for the same underlying entity that the upstream system published. So then you need to start to think about things like idempotency. So if there's one single thing you take away from this talk, it's to make sure you adopt some kind of structured payload for your events. One such way of doing that is the Cloud Events specification. It's come up quite a few times over the last couple of days. And there's various fields in here that can help us do various different really interesting things. Now, all these properties here aren't all required. These are just ones that I think are particularly interesting and particularly useful, at least in the systems that I've built. So you've got the actual data property. This is the actual payload of the event. You've then got the data content type. This tells the consumer what type of data to expect in that data property. Is it JSON? Is it XML? Is it protobuf? Is it Avro? You've got the trace parent. Again, this is an optional field, and we'll talk a little bit more about observability in the last third of this talk or so. But this allows you to pass around some kind of common identifier from system to system to system. Expiry time is another optional one, but one I find really valuable. As you're publishing an event, you can tell a consumer, well, when should you no longer worry about this event? If I was to order a pizza today and the kitchen service was to pick that up in 3 days, I'm probably not really that interested in receiving that pizza. You've got the actual time this event was published according to the producer. You've got a unique identifier which allows consumers to implement things like idempotency, to say, have I seen this event before? Yes, I have. I can get rid of that. And then finally, with this conversation around evolvability, about versioning, about allowing your subscribers to be able to deal with different versions no matter what messaging transport you're using, you've got the source and you've got the type. Now, the source tells a consumer where has this event come from. The type tells the consumer what type of event this is. And I think it's really important to include in that type what actual type of data is in that data payload. Here, this is version 1 of the order created event. This means no matter how the consumer consumes this event, whether it's a queue, whether it's a stream, whether it's a topic, whether it's a bus, however they've got that, they've got the potential to be able to deal with that change in a safer way. They can today be consuming order confirmed version 1. And the order service is going to start dual publishing version 1 and version 2. Over time, the kitchen service can translate over, and it doesn't matter if they're doing that by consuming from a completely different topic, or they're doing that for having some logic in their code to understand which version of the event they've just received. And remember, the events that you publish are the API of your system. So treat the events you publish, think about how you structure them, think about how you're going to evolve them as you move forward. So great, we can evolve our system now, fantastic. You've given yourself as a producer the potential to be able to make breaking changes in a relatively safe way. You've started to think about how you evolve your data structures. And you've given the subscribers of your events that potential, at least, to be able to safely evolve their systems at their own pace as well. So from an evolvability perspective, we've started to think about how we're going to evolve our data structures, think about versioning, think about how we're going to manage change. Once you make that change, though, of course, you're going to want to test it. Who finds writing tests their favorite part of their job, by the way? I always get at least 2 or 3 hands. It's amazing. I'm still yet to get 0 hands there. That's always my kind of expectation at this point. And before I worked at Datadog, I worked at AWS for quite a few years. And the number 1 question I used to get speaking to AWS customers was, how do I test an event-driven system? How do I test an asynchronous system? Which naturally led to the question, what types of tests should I write? Should I write unit tests? Should I write end-to-end tests? Should I write integration tests? Should I chaos test? What types of tests should I write? And for the purposes of this talk, I want you to try and forget about that kind of semantic argument of, is something a unit test? Is something an integration test? Focus instead on exactly what it is that you're testing. Because I kind of think what types of tests to write is the wrong way to think about testing, that semantic argument of what type of test it is. Instead, I think it's more valuable to ask why. Why exactly do you test your software? And to ask that same question in a slightly different way, and I want you all to take 3 or 4 seconds just to actually think about this. Why exactly are all of you building software? Why are you working in software? And just take a few seconds to think about that. Now, whilst I was preparing this talk, I've tried to think of a few reasons that come up for me, a few reasons that hopefully will resonate with some of you. The first of those is that you all want to be a little bit more like Scrooge McDuck. At least today, the software industry is a reasonably well-paid industry, right? So money's a good thing to have, and unfortunately, 2025, money still makes the world go round. Okay, slightly tongue-in-cheek, that one. The second reason I could come up with is that you all love building really complicated stuff. It feels good, doesn't it, when you get that thousands of microservices all deployed on that Kubernetes cluster. Frankly, for me, if I get a single app running on a Kubernetes cluster, I get kind of excited. We love building really complicated stuff, don't we? And I actually always find this diagram kind of funny, because the first part of my career, I was working on SQL Server integration services. Has anybody ever built SQL Server integration services packages? Some hands. So I was the guy building the midnight heroics, basically. I was the guy cursing the developers for building this complicated distributed system that then needs to be kind of pulled together. And even after doing that, I still spent the next part of my career putting cool databases in event buses in places where cool databases in event buses had no right to be. Okay, then first 2 are a little bit tongue-in-cheek. I'm sure for many of you, the reason you're working in software is because you want to have an impact on people. Regardless if you're building a 20-year-old monolith running .NET Framework 1 that runs under John in account's desk, or you are building this complicated set of hundreds of microservices running on Kubernetes, if the thing you're building doesn't do the thing it's supposed to do, what's the point? If it doesn't fulfill the requirement it has, if it doesn't fulfill the requirement that the business needs it to, then what is the point in doing it? And there was a really great talk at QCon London last year by Martin Thwaites. I'd really recommend checking out this talk if you're interested in testing and building more reliable software. And one of my takeaways from Martin's talk is that it doesn't actually matter if you've written hundreds and hundreds of tests that test every individual class, every individual property, you've got 100% code coverage. None of that matters if the system, the service, doesn't fulfill the job it's supposed to fulfill, whether that's an individual service inside a microservices architecture or a module inside a monolith. That thing will have a job it needs to perform. And when you think about maybe a more synchronous system, you think about the order service, think about what requirements does the order service need to fulfill? Well, it needs to be able to allow a user to create an order, and then it needs to be able to allow a user to go off and get the status of that order at a later point in time. And I'm sure whatever programming language any of you work in, I'm sure you can all kind of visualize a test that you would write to test this. You would have an instance of your app, you would make the post request, you would make the get request, you would assert on the get request, or something similar to that. This isn't the only requirement the order service has, though, is it? Because the order service also needs to notify other systems that an order has been created. And this notification is probably going to be sent to some kind of message transport, Azure Service Bus, Amazon EventBridge, Kafka, RabbitMQ, and maybe there's a subscriber using that event, maybe there isn't. So how do you assert on this thing that happens completely asynchronously that may or may not have somebody listening to it? I know what you're all thinking. You want to go back to that .NET Framework 1 monolith, don't you? Life was just so much simpler then with that little monolithic application. Maybe you're even regretting your decision to build an event-driven system. Now, there's a few patterns and practices that can help you here, though. So if you're building a system that's doing something like this, where you're manipulating state in some way in your system, and you're also publishing an event, you're probably going to be using the outbox pattern in some way. Who's familiar with the outbox pattern? I'm assuming most hands. Okay, cool. So for anyone who isn't, or anyone's watching this on YouTube, the outbox pattern is the idea that whenever you update state in your database and you want to publish an event, instead of immediately publishing the event, you just write that event to another table in your database, wrap both of them things in a transaction. If one doesn't happen, it means that the other one doesn't happen either. So when that post request comes into your order service, at that point, you've got the state updated in the database, and you've got the event written to another table inside your database. And then, of course, you've got this worker that's going to come along. It's going to come along and pick up all the events that need to be published, and it's going to go off and publish them. So one option you have for testing an event-driven system that uses an outbox in some way is simply assert on the fact that the record has made it to the outbox. Because then the order service has fulfilled its job. It's updated the state, it's stored the event in the database table. You can assert on that and just trust that the outbox worker is going to go on and do its job. And this is a great starting point. If you're in a place today where you just want to make sure that an event gets published, this can be a good way to start. But the requirement of the order service isn't to store an event in a database table. That's an implementation detail of the service. The requirement of the service is to notify other systems that an order has been created. So what other options do you have? Now, in an ideal world, when you're running tests against your system, you're going to be able to have some kind of completely ephemeral, completely isolated test environment, which means hopefully you're going to spin up this isolated unit that contains your order service. Maybe it also contains the database that you're using and whatever message transport you're using. Maybe you spin all this up in Docker Compose locally. Maybe you deploy this to an ephemeral environment in the actual cloud and then tear it all down again. It largely doesn't matter. In an ideal world, you're going to have this isolated thing that you're going to test against. So what I would always recommend you do is when you're doing this and you're running your tests, spin up one additional component of part of this system that you're going to test. I'd call that a test harness or a test subscriber. What you're doing here is you're spinning up an additional component that is behaving like a subscriber. It can be completely generic, and there's ways to build this in a really, really generic way. It's going to spin up, it's going to subscribe to all the events that your system's publishing, and it's just going to collect all those events in memory. It's then also going to expose some kind of API endpoint so that you can come along and say, give me all of the events that you've received for order or entity X. What would this actually look like in practice? So in your actual test, you're going to spin up this order service, all of them different components. You're going to make that initial post request to your order service. Hopefully, the order service is going to respond, and it's going to say the order number is order 12346. Don't ask me where the 5 went. I still need to update these slides. Hopefully, behind the scenes, this is going to then publish an order created event. Hopefully. That order created event is going to be published onto whatever message transport you're using, and then this test harness is going to consume that. It's going to subscribe to that event. It's going to store it in memory. It's going to store that in a cache, wherever you store that, doesn't matter. And then in your test, you can come along and say, hey, I'm going to assert on the fact that an order created event has been received by my test harness. So here you're now testing that your service is actually doing the thing it's supposed to do. You're testing that when an order gets created, that the event actually gets published to the actual place it's going to be published to in production, and you're just simulating the behavior of there being a subscriber downstream. Now, of course, this is only testing the happy path. It's equally, if not more important, to also test what happens when the system doesn't do what it's expected. And there's a reasonably finite number of things that you can predict ahead of time, if you will, for an event-driven system. An upstream system makes a breaking change. They didn't watch Layla's talk earlier, and they make a breaking change and don't tell you. You can test for that. You can inject an event that has a different payload than what you expect, and you can see how your system behaves. You can test receiving the same event multiple times. Most messaging systems guarantee at least once delivery, which means you might receive the same event multiple times. But even if you're using a messaging transport that guarantees one-time delivery, that still doesn't account for the upstream producer having a problem and publishing the same event multiple times. And you can test for that as well once you've got this ability to spin things up and put this test harness in place. Now, I know what some of you might be thinking. If I'm writing tests that are relying on this asynchronous process, I'm writing tests that are relying on this message going through this message transport that might take 100 milliseconds, it might take a second, does this not lead to incredibly flaky tests? Yes, it possibly would. I'm sure you've all been there where you've written a test and sometimes it passes, sometimes it fails again, then it passes. And this can be because this message is maybe on its way, but it's still inside the message transport somewhere. So if you're doing this, I'd always recommend implementing some kind of poll and loop and retry behavior inside your actual test. Which obviously leads to the question, how long should I wait? How many times should I retry? Because you don't want to do this forever, but equally you don't want to do this for not enough time to let the message actually flow through the transport. And there's actually a really easy way to think about this, because most of the services all of you are building will probably have some kind of requirement related to latency, to performance. Let's imagine the order service needs to process an order inside 300 milliseconds. Well, I'd base how long I wait inside this poll and this loop on retry on the actual requirement that the actual system has. If it's 300 milliseconds, maybe I check once, I wait 100 milliseconds, I check again, wait another 100, check again. If it hasn't received by that point, even if it was coming, I'd still broken the SLO of my service anyway. Now, obviously, all of this up to now has been focused on testing flow, focused on testing that an event flows through the system in the way you expect it to. But what about structure? Obviously, of course, that issue right at the start of the talk that I had was an issue of structure. It wasn't an issue of flow. The structure of the event had changed in a way that I hadn't predicted, I hadn't expected. And you can test for this as a consumer, but the extent of a test you can do as a consumer is probably that I'm going to inject a version of the event that has changed in some way, and I'm going to check that my system doesn't completely blow up and that the message ends up in a dead letter queue. That's probably the extent that you can test as a subscriber. But why can't we shift some of this to the producer? Why can't we test structure at a producer level? And most modern programming languages support the ability to parse JSON schemas and compare a JSON schema to the actual payload of the event. So here again, this is .NET code. It'll look reasonably similar in whatever language you're using. There's a schema that's stored alongside the actual tests. That schema is going to load up. We're going to run our actual business logic to generate the event, and we're going to check that the generated event, the schema of that event, matches the actual schema of the actual thing that was published. Now, you can take this a step further. If you've adopted some kind of schema registry, and that schema registry has some form of API to be able to parse that information, you can, instead of loading that schema from a local file system, you can load that schema from the actual schema registry. You load that schema from, here's what I've committed to publishing, because I've put this in my schema registry, and I'm going to compare that in my tests to what my business logic actually generates, to what my code actually generates. So here now you're in a position where you're both thinking about how you're going to evolve your data structures, thinking about versioning, thinking about how you structure your events. And you're thinking about now testing both structure and flow. And no matter how well you think about evolvability, no matter how well you test, you can write hundreds and hundreds of tests of all possible edge cases and all possible things that could possibly happen inside your system, things are still going to break. Things are still going to fail. Which, in my opinion, makes observability the most important part of building modern distributed systems. And I'm not just saying that because I work at Datadog. Because things are always going to go wrong. Things are always going to break. Right? And just to take a step back for a second, how do I actually think about observability? The observability is the ability to ask questions of your system. Questions that you didn't know you needed to ask from a location that is external to your system. Asking questions you didn't know you needed to ask. It's kind of a weird way of putting that, isn't it? What do I mean by that? Well, let's imagine you're a developer on the order service, and the order service has an outage. It has an outage because the database server runs out of disk space. So the database goes offline. So you're going to come along as a developer, you're going to hopefully give that database server more disk space, and then everything comes back online, and I'm sure it's probably a lot more involved than that. But let's assume that's what you do. And after that has happened, you're probably going to do some kind of retrospective, and you're going to probably put some kind of monitor in place, if you didn't already have that, to monitor the disk space of that server, which dramatically reduces the chances of that same problem happening again, because you're now monitoring for it. But in distributed systems, you're primarily dealing with unknown unknowns. Distributed systems fail in new and novel and interesting ways all of the time. Distributed systems are being updated frequently by lots of different teams, by lots of different people who've got different release cycles, different priorities, different pressures, different business environments, different users. There's no possible way you could ever begin to think you could predict all of the ways something can go wrong ahead of time. So building your system in a way that allows you to ask questions of your system, to play detective inside your system, is key to modern observability. But not only are you now dealing with distributed systems and unknown unknowns, you also chose to make your system event-driven. And in an event-driven system, cause and effect is incredibly hard to understand. Understanding the upstream systems that affect your system and the downstream systems that you're having an impact on becomes incredibly difficult. It's difficult because if you compare this to a more synchronous communication, you can reasonably easily infer here that the order service is having an impact on the kitchen service. The order service is making some kind of call that's going to travel across the network. It's going to sit there and wait. It's going to be blocked until there's a response. The kitchen service does its work and hopefully eventually responds with something that looks like success. In an event-driven system where you've just got producers producing events, consumers consuming events, they don't really even know that each other exists. How would you even begin to understand what thing that you do has an effect on another thing downstream? And that's where, in my opinion, distributed tracing is the most important part of observing event-driven systems. And just to level set on a bit of terminology, just to make sure we're all on the same page, the top level is a trace. A trace is the end-to-end flow of a request. And a trace is made up of lots and lots of different spans. These spans can span multiple different back-end systems, and these spans can also have tags or attributes. And just had a little bit of a caveat to what I've just said. When I say distributed tracing is the most important part of modern distributed systems and observability, I mean distributed tracing with lots and lots of context. It's context that is the key part of modern observability. And I like to think of context in two different ways, two different parts. The first part is technical context. Technical context is the context that's familiar to all of our systems, no matter what domain or what business they're operating in. Things like the HTTP route, the HTTP method, the HTTP status code. All of these things are common to all systems that are using HTTP. And OpenTelemetry actually publish a set of semantic conventions for messaging spans, which is a really long-winded way to say best practices. This gives you a set of tags and attributes and spans that you should always have inside a system that deals with messaging. Now, this isn't an exhaustive list. There's a few here that I just wanted to call out to kind of give you a flavor of what these spans are. So you would always have a span. If you were processing a message, you would always have a span that is process, the name of the event type that you're processing. Equally, if you're publishing, you would have a publish name of the event type span. And then inside that span, you would have a bunch of attributes, things like the operation name. Are you sending? Are you receiving? Are you processing? The messaging system that you're using, are you using SQS? Are you using Kafka? Are you using SNS, a service bus? And then the destination or that you're sending to or processing from. Here, this is the order confirmed queue. And then there's another couple here that aren't necessarily in the open telemetry semantic conventions, but two that I've always found incredibly useful when you've been doing things like this. The version of the event that you're either processing, publishing or consuming, and the type of event that you're processing, publishing or consuming. How does this benefit you though? Once you've got this technical context in place across all of your systems, how does this actually help? Well, it allows you to start to draw really interesting insight. It allows you to get a really high-level look at exactly what your system is doing because you've got this common set of telemetry. You can look at how many spans are there in the system for publishing, how many spans are in the system for processing, for receiving. What are the size of these messages? How old are these messages? And it also allows you to do really interesting things in your observability backend where you can say, actually, show me all of the telemetry where the operation name is process and the message type is order completed. And with a little bit of aggregation, I can group that up, and now I've got a list of all of my consumers. I've now got a list. If I'm the developer of the order service, I can now see all of my downstream dependencies by just querying the telemetry. I know that actually it's only the loyalty service who cares about this order completed event. Now, I said there's two parts to context. The first is the technical context, the context that's familiar to all of us. OpenTelemetry gives us a really good way of thinking about what that should look like. But then there's also the business context, the context that is unique to whatever your specific domain or business is. Imagine your support person comes to you and they say, we've had a customer on the phone, they've placed an order, that order's gone missing. Where is it? We don't know. They've never received it. Adding business context to your telemetry then allows you to ask the question of your system, show me all of the telemetry related to order 1, 2, 3, 4, 6. You can look at your telemetry and say, okay, it made it to the order outbox maybe, and it never left the outbox. So, well, it looks like there's a problem with the outbox somewhere. And I think you can even start to take this a step further maybe. Because as well as adding the custom business context, why can't we actually start to think about building documentation of our system from the actual telemetry? What if we were to start tagging our telemetry with the actual structure of the event that we received? And then if you're looking for what's the structure of the order completed event, rather than relying on some documentation that may or may not be up to date, depending if the developer decided to update it, you can go and look at your telemetry and see what is the structure of the actual order completed event that is actually being published in the system. Now, there's a quick disclaimer I always like to put in here. What I don't want to happen is in 6 months' time, all of your security teams are on the phone to me and they're saying, James, one of our developers came to your talk at EventCentric, they've took your advice really literally, and now Datadog's filled with all our customers' credit card numbers. Please, people, do not send PII data to your observability company, to your backend systems. We don't want it, you don't want to do it, just please don't do it. So when I say add business context, add as much context as you can, as you can, meaning inside your specific regulations, industry, whatever that means to you in terms of a data protection setup. So distributed tracing might seem like it's a little bit of a silver bullet, right? You put this distributed tracing in place, you can see how a message flows around, you can see the systems that it passes through. This is an example of a distributed trace from plant-based pizza. Every different color on there is a different service, a different message transport, and you can really nicely see how this event flows through the system. And if you zoom into this, you start to have a bit of a closer look. You can even start to see what message transports are being used. So this happens to be deployed to AWS. This event got published to an Amazon EventBridge event bus called dev.orders, and it spent 294 milliseconds inside my event bus. It then went to a queue and spent 117 milliseconds inside a queue, before eventually being picked up and processed. Now, in your application code, there'll be a little bit of manual work you need to do here to kind of infer these in-flight spans. But you might look at this and think, wow, this is really useful. I can see each individual transport. I can see how a message flows around. It's fantastic. If we look at this image again, though, you've got these really long purple bars in the middle. And you've got this initial request that completed in about a second, and then this big, long purple thing that took over 10 seconds. What is that? And it kind of confuses the whole graph, doesn't it? Because you're thinking, well, this initial API request might have completed in about a second, but the trace is now a 10, 11 second trace. Is that really right? And many of you will be in situations like this, where you've got something that happens that kicks off a long-running business process of some kind. That business process might take seconds, it might take minutes, it might take hours, days, weeks, whatever it is. You've got this long-running process that runs. Or maybe, to give you a slightly different example, maybe you're doing some kind of batch job, some kind of batch processing. Maybe here you've got an analytics service inside Plant-Based Pizza, and that analytics service is queuing up all the order confirmed events that happened that day. Once a day at, say, midnight, it picks up and it processes all of the order confirmed events. Well, if you were to propagate your trace context to get that really nice, pretty flame graph, well, each individual step of your daily job would then appear in the upstream trace, which isn't particularly useful for you trying to work with the analytics service, but it also really confuses the upstream trace as well, because the team working on the upstream system might have a trace that ends up being 16 hours long if someone's ordered pizza for breakfast, which should be a thing, if you ask me. Now, how can you deal with this? How can you manage this? How can you get around this? How can you deal with this? We still want to understand cause and effect, but we think propagation might not always be the answer. And that's where span linking comes in. With span linking, instead of propagating the trace context, you say this span in this trace is linked to this span in this trace. That keeps your traces completely independent, completely separate, while still allowing you to understand that cause and effect, which naturally then begs the question, which one do I choose? Do I choose span linking, or do I choose trace propagation? And the simplest way, I think, to think about this is to think about the unit of work. Think about what is useful to you as a developer. So if you're a developer on the order service, understanding that when an order comes in, it hits the API, it maybe gets saved to the outbox, then something picks it up from the outbox and publishes it to some kind of message transport, it's probably useful for you as a developer of the order service who owns both all of them things to understand that end-to-end request flow. But maybe that event then gets picked up by the kitchen service, and the kitchen service has its own internal processes, its own internal business flows. Well, you don't really care about that necessarily. You don't care what happens inside the kitchen service. So a general rule of thumb is to propagate inside a domain, propagate inside a bounded context, and link between different bounded contexts. Another slightly different way you could look at that is to propagate if you're orchestrating, and link if you're choreographing. That's a word, yeah. Of course, that's a rule of thumb. That's not always the case, but just think about that unit of work. Think about what is going to be useful for you as a developer. And whichever way you choose to do it, do something, because once you start to do something, it allows you to start to understand how the different pieces of your system fit together. It allows you to understand that you're a developer of the order service, and upstream of you, you've got the inventory service, and downstream of you, you've got the loyalty service, and somehow also the inventory service is both upstream and downstream dependency. It allows you to understand how things move around your system. It allows you to ask questions of your system. Now, a lot of this so far has been talking about tracing, distributed tracing. And I think distributed tracing adds the required nuance to this statement. And you'll often hear this when people talk about event-driven architecture, that services are unaware of the downstream consumers of their events. Services are loosely coupled, and that's fantastic. And whilst this is technically a true statement, it's a really dangerous thing to think without really thinking about how you're actually going to understand this in the real world. Because although technically they're really unaware of each other, you still as a developer want to understand how these things work together. Now, that's a lot about tracing. Does that mean things like metrics aren't actually useful anymore? Because traces give us this really nice flow of an individual request through the system. But what is useful to think about when you kind of step back and look at the bigger picture? And OpenTelemetry actually also publish a set of semantic conventions for messaging metrics, best practices, for metrics. And there's a selection here of some of the metrics that OpenTelemetry recommends, some that I've just found particularly useful as I've been building event-driven systems. Things like the queue depth. How many messages are there in the queue? If the queue depth is growing over time, that probably means that you can't deal with the throughput of the upstream system. Equally, if this is a dead letter queue, this probably means that there's a problem somewhere in your system. You've got the number of messages that you've processed, but also the number of messages that your system's consumed. And actually, importantly, the size of those messages as well. Because understanding the size of the message that you're receiving can be a pretty good indicator. If there's a sudden spike in the size of the message, either up or down, that can indicate that probably there has been a change to the structure of that event somewhere. That may well mean that you need to go and make a change to that, to your code. We've got the message age. This is kind of related to the queue depth. This keeps track of how old is the last message that you processed. This can help you understand, again, if you're dealing with the throughput in a performant way. If the message age is growing over time, that means that, well, probably you're not really keeping up with the load that's coming through your system. The in-flight latency, how long does a given message transport, how long have the architectural decisions that you've made in terms of your chosen technology adding to the overall latency of the system? And then the kind of more obvious ones, the number of errors and the type of each type, the count of each type of message that's flowing through the system. And if you've got all that technical context in place that I talked about earlier, a lot of these metrics can actually be inferred simply by just querying and aggregating your trace data. You don't necessarily need to be generating traces and generating metrics. You can kind of infer everything from them traces if you've got that context in place. Which of these are important to you, which of these you choose to alert on, is obviously going to completely depend on your specific business. If you really value end-to-end latency, then maybe message age and in-flight latency are useful to you. If you really value building a really resilient, really reliable system, then maybe the number of errors is the thing that you care about. And another thing that's really, really important is that actually success is also a really important metric. Imagine that your system, on average, processes 10 events a second, 10 messages a second. And then all of a sudden, your system starts processing 0 messages per second. Now, there might not necessarily be any errors in the system, but the lack of success can also be as useful an indicator as the number of errors. Now, of course, I realize that actually none of you are actually developers for plant-based pizza, and I always like to visualize in my head that if you were, you'd all get free pizza, which would be amazing. I wish I could give that to at least those of you who had your hands up. I suppose the rest of you wouldn't really want that, would you? So what does this actually mean for all of you? When you go back to your day jobs tomorrow, you go back to your day jobs on Monday, what does this actually mean for you when you go back to your system? The first thing, think about how you structure your events. Whether you adopt the cloud event specification, whether you use the metadata data pattern that Sheen talked about yesterday, think about the structure of the thing that you are publishing. Remember, the public events that you send out are the API of your system. People will consume them, people will use them. Think about how you're going to evolve that system and evolve them data structures over time. Secondly, remember, context is king. It's context that makes observability really valuable. It's context that allows you to ask the questions of your system, to understand when things go wrong, well, actually, why did they go wrong? Where did they go wrong? How did this thing break? And finally, think about things both at the micro level. Think about how an individual request flows through the system, but also don't forget about the bigger picture. Don't forget about the insight you can draw from aggregating your telemetry and looking at these kind of bigger picture numbers for exactly what is going on inside your services in your system. Now, as you've probably all discovered over the last couple of days, if you didn't know that already, event-driven architecture is an incredibly powerful pattern for building modern distributed systems. It gives you all the benefits of microservices, whilst also giving you that loose coupling and allowing systems to evolve independently. What I hope you've got from this talk is that it's not just a silver bullet. Event-driven architecture is not without its trade-offs. It can kind of lull you into a false sense of security, making you think you're incredibly evolvable, even though actually you really, really aren't. It can trick you into forgetting about who your upstream dependencies are and who your downstream dependencies are. And before you know it, you've broken a system that you didn't even know existed, which is not a particularly good way to build reliable systems. Honestly, people, it's not really a good way to make friends either. So if anyone's interested in diving a little bit deeper, I've got a course online from zero to hero event-driven architecture. It takes you from what is an event to building plant-based pizza. You build that throughout the course. That link's there. All the slides, if I go over this side, all the slides and any links and any resources are all available on my website. The link to that is there as well. Thank you all very much for coming out. It always really surprises me when all these people turn up to hear me ramble on for 50 minutes. So genuinely, from the bottom of my heart, I really appreciate all of you. I will be around for questions. If you've got any, we can do them live now. I'll hang around here if you don't want to put your hand up. So thank you all very much.